Hello everyone, I hope you guys are doing good. Okay, so in today's lecture we're going to be talking about the electric field. We have studied about Coulomb's law, we have studied about electrostatic force and all. Now it's a very important part of this chapter. I mean, like, this is going to be along with you for the next 2-3 chapters, like capacitors. We're going to be talking about the electric field intensity, potentials and all of the stuff, so this is going to stick with you for a long time. So probably I'll be taking up 2 to 3 lectures on this topic. This is a very crucial topic. So in today's lecture I'm going to keep things quite basics. So get the feel of electrostatic field, electric field, and then probably we can go on and solving some good question. Now the point is, how this electric field impact your physics? How does it impact your study of electrostatic? Well, understand one thing. I'm sure you guys must have felt it so far that in this class 12th, whatever we're studying, we cannot see it. Like the force, we cannot see the force coming up to us, right? We can only experience it, and that's a fact. We cannot see things happening, we can only see the consequences, the result of that. Let's say, for example, in the gravitational chapter, you must have studied that, one body pulls another object, another body. They're not directly connected with each other, still they pull each other, right? There should be some force of attraction, there should be some means by which they attract each other. But we don't see that means. And same goes along with in the electric field as well. You might have heard that, a charge pulls, repels, attracts. I'm sure we have discussed in the first lecture. Now we're going to talk about how it all happens, right? So how does a charge kept at one distance probably attracts a charge kept at far away from that? There should be some waves, probably, there should be some lines of force which impact the another charge present around that, isn't it? And that line is called electric lines of force. So basically we're going to see this in 2 parts. The first part is that one charge creates a field around it. Let's say a very simple example. If you're standing in front of me, you can hear me because I'm producing sound energy, right? It means I'm producing some sort of energy which is experienced by you in different forms. It could be sound energy, could be probably mechanical energy, could be probably the light energy, anything else, So likewise, a charge produces an electric field around it which is experienced in terms of force by the another charge kept in area around that, right? And that's called electrostatic force, isn't it? So how it translates to that particular point? It happens in terms of waves. And I'm sure you guys must be aware of the fact that a wave travel to speed almost equivalent to the speed of light. So we normally take as speed of light. So let's say if I have a charge probably plus q over here, it must have created some sort of elements around it which would have attracted or let's say repulsed. Let's say if I have a negative q charge present in its close by area, it will experience the force of attraction, right? It means it has created something which attracts this charge. If this could have been a positive charge, it could have been repelled, right? And that is called electrostatic field or electric field in very general. And we're going to be talking about that today. And we're going to be talking about the properties and how it all impacts your study about the physics. Okay, so I'm sure you can see the headings electric field. So basically it is a line of forces, which impacts the another charge kept in that particular area. How does it impact? In terms of force. Basically, electric lines of forces are the carrier of energy. When we talk about the electric lines of field or the force, it's all about the energy transmission. Okay. Now, a very basic simple thing I need to understand that if I have a plus q charge kept over here, let's say I have kept a charge plus q over here, it's going to create some field. Well, the field is going to be spherically outward, or you can say radially outward, like this way, Fair enough. Now, if I bring another charge, not that huge, which is going to impact this charge itself, it's going to be small charge. Let's suppose if I bring another plus positive charge over here in this area, let me call it as a test charge. This test charge is quite ordinary, and at certain point of it becomes really important. What happened? This is influenced by these lines of forces. Okay, and it will be having some impact on this. It might feel a force, probably that could be a repulsive force, isn't it? Yeah, so this lines of field has propagated to this charge and the velocity of the propagation should be equals to, let's suppose, c. Let's assume that the distance is d, then the time taken would have been equals to d by c. So one thing I want to make clear to all of you, that the moment I have a charge over here, this will not feel its presence. It will feel its presence only after this much of time. Fair enough? So the propagation of the wave is happening with the speed of light. Fair enough. That's a basic thing. So when we talk about the electric field, I'm not going to write on the board, you can just note it down. So it is a region, it is an area, okay, around a charge in which another charge can feel a force by that charge. That's called electric field area, isn't it? Yeah. Now, and that's called electric field itself. Where is my duster? One second, guys. All right then. So now we're going to talk about the appearance of electric field, its structure and its impact on the another charge. So what happens, let's suppose if I have a plus q charge over here, as I've told you, it originates from the plus positive charge. We assume that electric lines of field are positive in nature. That's one thing we need to understand, because it is originating from a positive charge. Okay, if it is originating from the positive charge and it's going along, and it is not dependent on any other charge. One particular charge can create a field around itself. We do not need to have probably multiple charges to have this, right? So it is quite independent of another charges, right? Okay. Now, if it is coming out of it, it must be terminating at a certain point. Let's call that point as infinity. So the electric lines of field, these are the electric lines of field or force, whatever you want to call it. It originates from a positive charge and terminates to infinity. That's the first point. You guys can note it down, pause the video. Second thing, if I have a negative charge over here, the electric lines of field seems to be, terminating at this particular charge, and that's how it would look like. So from here I can understand that electric field of line terminates at negative charge, right? So now if I correlate these two things, I can understand that electric lines of field originates from a positive charge, or if these lines are coming, they're supposed to be coming from infinity, isn't it? So I can say that electric lines of field originates at the positive charge or at infinity. That's going to be the first point, guys. Please note it down. Electric lines of field is, they originates from a positive charge or from the infinity. I'm keeping these two charges very separate, it's not like I've kept them quite, just a blackboard constraints. Okay, the board constraints. So these fields you can see are terminating its negative charge. It means they would have originated from certain point, right? Well, that point could be assumed to be infinity. So now I can say that I have 2 points. First, as I've told you, that electric field of lines can be assumed is originates from the positive charge and terminates at infinity. Let me put it here. Or it terminates at a negative charge or originates from infinity. Fair enough. So I've kept these two charges quite apart. These are two different perspectives, and we have understood that how the electric fields of line originates and terminate. Okay, let me do one thing. Let me get these two charges close to each other. All right. If I do that, let's see what's going to happen and how the field going to react to this particular situation. Let's say, guys, if I have a positive charge being kept here, and let's say plus q, and a negative charge, negative q, kept over here, then the field lines would originates from here and would terminate to this negative charge. Okay, we know that a point charge originates or radiates the field in a spherical way. So that could be the pattern which we can see. So this could be the pattern that we could see in these kind of cases. That's how it's going to look like, right? That's how it's going to look like. It's going to go and it's going to come back and terminate over here at negative point charge. Okay. Now the second thing which I want to bring up over here, instead of plus q, if I would have had, let's say, 4q, then would we having the same number of lines coming out of it? Probably no. So it actually depends upon the amount of charge. Bigger the charge, more is the electric lines of field. I think I've told you in the very beginning, the electric lines of field is nothing but is a resemblance of energy. For example, let's understand this very simple example. If I have a magnet, a small magnet, it would be attracting the next, probably the iron piece or maybe another magnet with certain amount of force. If I have the bigger magnet, that's going to attract by the huge amount of force, right? With a greater amount of force. It means the magnetic property of that particular magnet, depends upon the size of the magnet. Likewise, if we have a higher charge, a greater charge, it's going to create more lines of field. So I can say that electric lines of field is proportional to the value of charge. That's the second point you guys should note it down. If I would have had, let's say, probably 10 Q of charge, that would be producing more amount of electric lines of field compared to what is produced by a positive Q charge over here. Right? So electric lines of field is proportional to the number of charge, the value of charge over there. All okay? Now let us talk about the mathematical aspect of that. Let us understand how to define it. So far we have understood the basic of electric lines of field, and we have seen how it all propagates in the medium. Now if I try and define the electric lines of field and the electric field intensity, probably it will be defined as the amount of force experienced by a test charge present in that electric field. Let's say if someone is speaking a bit at certain amount of sound, I would be hearing him at certain amount of pitch. If someone is speaking loudly at higher amplitude, I would hear him quite loud, right? So the same thing. So the intensity of the sound produced by the person would be decided by the way I'm actually receiving it. The same goes along over here. So electric field strength or electric field intensity is defined as the force experienced by a test charge present in that electric field. If it is more, it means the field strength is higher. If it is less, it means the field strength is lesser. Fair enough? So the electric field E is defined as the force experienced by a test charge present in that particular area. We're going to be talking about the vector forms of this as well, but as of now, let's try and keep it as it is in very normal situation. So the unit of this should be Newton per Coulomb. Later on, I'm going to define electric field intensity in terms of potentials. Then we're going to come across a different unit of that. As of now, Newton per Coulomb is going to be the unit of the electric field. Okay, already we have learned about the force from the Coulomb's law in the previous lectures. All right, so can I just say that, okay, let's have a charge Q over here. It's actually creating a field around it. Let me have a test charge Q naught over here at a distance of, let's say, D. I just want to find the force experienced by this Q naught over here. Fair enough? We know that the force at this particular point F is given as K Q naught over D square. From Coulomb's law we have already seen this. So this is the force over here. Now how much force is experienced by this charge over here? So that would be force experienced by this test charge. Well, that should be K Q naught over D square times Q naught, cancelling this one, and that's going to be K Q by D square, and that's nothing but your electric field over here. So far we have seen that it's all about the force experienced by a charge. Force has a direction. It means the electric field will also be having some direction. So electric field is a vector quantity. It's a vector quantity. Vector quantity. Fair enough? Now let me write this in the vector form. Let's quickly go ahead and put it in the vector form. I think I've told in the previous video. If you guys have not seen that video, see how to write the vector form of anything. Let's suppose A in the vector form should be K Q over R square, and I need to write the unit vector over here. That would be given as, let's keep it as a magnitude. I'm going to have R vector over R magnitude. So what I'm going to get, electric field in the vector form should be K Q over R cube, okay, into R vector. Well, this charge is the source charge. This is the source charge, because the test charge is experiencing the force. So this Q is the reason of this electric field being created around it, right? This should not be confused with the charge on which the force is being experienced. No, this is the source charge which is creating the field. Fair enough? Now, what are we going to do now? We're going to see some sort of examples, and we're going to work out on certain question to understand this properly. I'm sure by this time you must have got the feel of what is the electric field, how does it impact the study of electrostatic, and its dimension, of course, and its nature and the direction. All right, let's see some question based on this. All right, let me just erase this. All right, then let's see the electric field because of a point charge. That's the first thing. You make the heading electric field due to a point charge. That's the first thing that we're going to be studying now. Let's say if I have a point charge Q over here. Okay, now let's say I have another test charge being kept over here at a distance of, let's say, R from this point. I need to study how much will be the electric field at this particular point. Okay, well, I know that the force on this, let's say both are positive in nature. I'm going to put the positive sign. The force should be in this direction, force electrostatic. Fair enough? Now, the electric field at this particular point should be given as the force by the test charge Q naught. Okay, the force, we know that that's going to be KQ Q naught over Q naught is going to be KQ. Okay, I'm sure it's going to be KQ by R square Q naught. So I'll be having KQ by R. That's a very fundamental thing. Okay, that's going to be the, okay, let me just get the duster. That's a electrostatic field or electric field due to a point charge over here. So KQ by R is the KQ by R square. Sorry, that should be R square due to the sorry about that, due to a point charge. Now, as we know that electrostatic field is a vector quantity, so it should follow the vector rules of addition. So when we have the multiple charges coming up together, then it's going to follow the principle of superimposition. So I'm going to show you one example based on the superimposition of the principle, superimposition principle. Okay, let's say I have a charge being kept here on an equilateral triangle. Let's say let the side be A. Let's say if I have a plus Q charge over here and minus Q charge over here. This is an equilateral triangle with side length assume as A, for example. I want to know the field at this particular point. Let's have the Q naught charge, test charge over here. That's my test charge. Understand this thing? That is a test charge. Okay, now let's understand this. It's a positive, then the electric lines of field should be here in this direction. Let's assume this is E1. This is negative and positive, as we told you. Okay, before that I want to tell you something about that. Let's suppose electric lines of field is existing in this particular direction. Let's say we have electric lines of field E naught in this direction. If a positive charge is kept in this area, let's say positive charge Q, then as we have seen that electric field is originating from the positive charge, so we assume this is a positive, so this will be having a force, experiencing a force in this direction. Okay, now since we have seen that E is equals to F by Q, it means the force on the charge should be Q times of E. So this should be experiencing a force in this direction, that should be Q times of E naught as on. If I would have had a negative charge over here, then the force should have been in this direction, and that should have been equals to QE naught in this particular direction. So electric field of lines is always assumed to be a positive charge carrier. Okay, having known all this stuff, I can actually understand that the electric field on this charge, because of this negative charge, should be along this. Let's say this is E2. Magnitude wise, both of these going to be equal because the distance is equal in both the cases. Still, let's keep it as E2. Okay, now the resultant of these two should be obtained by the vector rules. Well, that should be somewhere like in this direction. Let's suppose E net, and that's what we have to calculate over here. All right, no problem. let's figure out the angle between them. It's an equilateral triangle, so 60, 60, 60. Let me put it 60 over here, 60 over here, and 60 over here. This angle should be 120 degree. All right. Now the value of E1 should be KQ over A square, and the value of E2 should be KQ again over A square. All right. I've actually represented the direction, so I don't need to keep the negative sign over here. That's one thing you guys need to understand. I'm not getting in the vector form. The direction is already mentioned over here. Now the resultant should be E net. E net should be root of E1 square plus E2 square plus 2 times of E1 E2 cos of 120 degree among. That's what we have over there, right? So the value of this should be, since E and E both, let's suppose that's equals to E, because both of them are equal. So I'm going to have E square plus 2E square plus cos of 120. Well guys, cos of 120, how much is that? I'm sure you guys must be knowing that the cos is going to be negative in that quadrant, because in second quadrant cos is negative. Cos of 90 plus 30 is equals to nothing but negative of sine 30, right? Well, that should be how much? Negative of E square. Let's okay, one second. E square plus E square. Okay, let me just correct it. This should be both are equal. So 2E square minus 2E1, or we can say E square cos 120 is going to be how much? 1 by negative 2. I have put already negative sign over here. Tick tock, I'm going to be having how much? E naught square. That should be equals to E itself, right? Cos 120. Cos of 90 plus 30. That's going to be minus of sine 30, and minus sine 30 is 1 by 2. I'll be having E square. Okay, fine, fair enough. So answer should be E, and the value of E is already known to me, right? So you can see that the net electric field would be in this direction, and that could be easily obtained by this vector rule, right? Okay, let's go to the next question. Now let's see example 2. Let us try and find the electric field at the center of a circle, triangle, equilateral triangle. Let's say I have an equilateral triangle, let's say A, B and C, and I have placed certain amount of charges over here. Let's say plus Q and plus Q. I want to know the field at the center of this triangle, that's centroid over here. Alright then, if I have the test charge Q0 over here, the electric field because of this should be in this direction. Electric field because of this should be along this direction, let's suppose, and the electric field because of this should be in this direction. Okay, now knowing the fact that electric field is a vector quantity, we need to get the vector components of this. If it is an equilateral triangle, the angle is going to be 60 60 and this is going to be 30. Okay, now this electric field, it will have two components, one this way, one this way. If it is 30, even this is going to be 30, so we're going to have E cos 30 degree and we're going to have E sine 30 degree. Okay, let me use a different color for this electric field. If this is going to have some field in this direction and some field in the topmost direction. Even this is angle going to be how much? 30 degree. So this is going to be E cos 30 degree and this is going to be E sine 30 degree. Well, these two are going to cancel each other, right? So the net electric field will be in the top direction and in the downward direction. So the E net at the center of this should be 2E sine 30 degree minus E. I hope you guys agree with this, right? The values could be anything. E downward and two components of this and this electric field are coming upward. So the net field should be 2E sine 30 degree minus A, right? Let's quickly see one more example. Let me just erase this up quickly. Chalo. Alright then, let's see. I have this XY plane. I have a charge, let's say 3 coulomb over here at a distance of R, let's say probably I'll be having a minus 3 coulomb here, and let's say probably plus 3 coulomb over here. Let's try and find the electric field at this point origin. So the question is, find E at origin. Let the distance be r, equal distance. Let's try and do it. Alright guys, what do we understand that? Let's suppose I have a test charge Q naught over here. Because of this, let's say I'm going to put a plus 3 coulomb of charge over here. Then the field should be in this direction. It's a negative charge, then the field should be in this direction itself, right? So because of this, if I assume this is E1, then because of this also it should be in the same direction, let's say E, because the distance is going to be same. It's a positive, then the field at this particular point, because of this charge, should be along this direction, right? Let me define some angle. Let's say this angle is 30 degree. Let's say this angle is 30 degree, and let's say probably this angle is 30 degree. I'm going to use the vector property over here to find the net electric field at this particular point. Okay, at this point, because of this charge, let's say I'm putting a point, let's say A, B and C. The electric field at this particular point origin, let's say O, due to this charge at point A, I'm assuming that to be E1. That should be K Q, which is 3 coulomb over here. I'm going to write 3 coulomb. Distance is r square. E2 is in the same direction because of this charge. So E2 should be K, again the same charge, 3 coulomb over r square. And this, because of this electric field, let's suppose E3, though they're going to be equal, I'm just putting the different denomination for that. E3 should be K, 3 coulomb of charge by r square. The point which I wanted to bring out over here is the vector component of this. Okay, one field, the net field over here in this direction should be E1 plus E2, and in this direction we should be having E3. So the resultant of this should be in this direction. Okay, let's try and see. If it is 30, this is going to be 30. Let's try if we're getting some sort of cancellations or not. Okay, so certain amount of field because of these two field would be coming in this. So this is going to be, and since we know E1 and E2 both are equal, so let's say E1 equals to E2, that's equals to E. So this I can write as 2 times of E. So we'll be having 2E cos 30 in this direction, and in this direction we'll be having 2E sin 30. And over here, due to this E3, which is E again, let's say equals to E, even this is equals to E. In this direction we'll be having E cos 30 degree, and downward I'm going to put one more thing, it's going to be E sin 30 degree. Now we're going to be having some sort of field along this way and something along this way, and we're going to find the resultant of that, right? Probably I could have kept different angles and all, that's okay, no problem. So the net field along X, so I'm going to put EX should be 2E sin 30 minus E cos 30, right? That should be 2E sin 30 degree minus E cos 30 degree, and EY, that is along the Y coordinate, negative Y, downward. That should be 2E cos 30 plus E sin 30. I'll be having 2E cos 30 degree plus E sin 30 degree. I know I can find the resultant of these two. So the resultant that the E net field should be how much? E x whole square plus E y whole square and the root of that, because the angle between these two is going to be how much? 90 degrees. Cos 90 is 0. Rest is just a piece of calculation, so you can put on the values, you can get the answer, right? If you guys have any sort of problem with this question, do let me know in the comment box. I would be happy to help you out there. But I'm sure you guys have understood. I'm going to recap it very quickly. I found the electric field because of this, that was coming in this direction. Because of this, that was coming in this direction again. I got the sum of that. Knowing the fact that the distance are equal, so all the fields will be equal. E1 equals to E2 equals to E3. I assumed that's P equals to E. Then the field, because of this positive charge, should be in this direction, right? Now we have defined the angles, so probably I found the value of this because of this field, net field, which is E plus E, which is 2E, right? A certain amount of this would be acting vertically down and certain amount of that going to be actually in this direction, and because of this we're going to be having something in this and something in that. All right, we had the net field 2E sine 30 minus E cos 30, and downward we're going to be having E sine 30 plus 2E cos 30, and the net would have been coming in this direction. I can easily find using this vector rules of addition, right? I'm sure you guys have understood this. Okay, what we can do now, we can mix this problem with some sort of like kinematics, like projectile and all. So let's see one such question before getting into more study about the electric field because of ring, because of disk, because of infinite line, because of probably on the dipole. One more thing I want to tell you guys, I'll be discussing the field because of dipole at the end of this lecture, and that's important. Okay, so just watch all the videos. Meanwhile, let us try and do some more questions. Let me just erase this up. Electric field on axis of a circular ring. All right, on a circular ring. Okay, now let's have a ring over here. Let's have a ring at the center O, having a radius of R. I want to find the electric field, let's say at a point P, distance R from the center of this ring. Okay, let's assume that the charge on the ring is Q, radius is R. Okay, I'm going to find the field at this point P because of this ring. Okay, I need to understand that this is not a discrete charge particle, right? It's a continuous charge particle, so we need to know how to do the integration and all, and I think I've discussed that in the previous videos, guys. You can check up in the Coulomb's law. Okay, let's choose a small charge over here, small length dl, having a small charge dq over here. Then the field because of that charge, okay, let me make a straight proper line. Okay, that should be in this direction over here. Let's suppose that is a small de. Well, this d will have two components. Let's suppose this angle is theta, then this is going to be theta, then this is going to be de cos theta, and that should be de sin theta. Well guys, there should be an equal charge particle over here which will be compensating on this d sine component. Let's say for example, I'm going to produce that to you people. Let's suppose again I'm going to have equal and opposite length over here. Well, that should be somewhat like this, and even this is going to be de, and this will have some de sine theta which is going to be compensating on that. So the net field should be along this direction, right? So ultimately what we're finding is the field should be along the axis, and that's going to be de cos theta. Okay, let us quickly find the value of de cos theta. Well, de should be k dq, let's say dq over, let's suppose the distance is r, small r, that should be equals to r square plus x square under root. So that should be r square plus x square under root. I'm actually trying to find d cos theta. So the de cos theta component should be equals to k dq over r square plus x square root of that into cos theta. Well, cos theta should be x over this length, that should be x over r. R is nothing but r square plus x square, isn't it? Well, this should be square of that, so this part will be nullified. Okay, a root of that. So ultimately what I'm going to get is, I'm going to put this part of the board. Okay, let's say, so okay, some obstacles. So de cos theta should be k dq x over, that should be r square plus x square to the power of 3 by 2. If I'm going to integrate this, I'm going to get the net electric field. All right, no problem. So I'll be getting the constant out of it. So kx over r square plus x square to the power of 3 by 2 is going to be constant, coming out dq. Well, dq should be from 0 to q. That should be the limit. So what I'm going to get is k x over r square plus x square to the power of 3 by 2 times, this is going to be how much? Q minus 0. That's going to be q. So the net electric field should be k cube x over r square plus x square to the power of 3 by 2. Guys, let me tell you one thing, you should be remembering it like anything, because I'm going to be using it quite some time in the upcoming lectures. So you just have to mug up this fact that the electric field on the axis of a ring having a charge q with a radius r at a distance of x is given as kqx over r square plus x square over 3 by 2. Just mug up this fact. It's really crucial, and it's going to be useful in a lot of questions, upcoming questions. Okay, let's see one more question over here, guys. Let me just erase this stuff. Okay, having said this, that electric field is equals to F by Q, I can say that F is equals to Q times of E. Let me introduce a little bit of kinematics over here, and that's going to be the question for the day, and then we're going to go and talk about more questions and more sort of fields about this. So far we have spoken about the electric field because of the point charge and a ring on the axis. Okay, let's quickly see. I'm going to have an example for you guys. Let's say a body is projected like this. It will cover up this stuff and all, you know. Let's say the velocity with which it is projected is 20 meter per second initially, making some angle of, let's say, I'm gonna keep, let's say keep it 45 degree, no problem. Okay, now there exists an electric field in this direction, E, okay, in this direction, right? And I'm going to take the value. Let's suppose the charge is 2 into 10 to the power of minus 6 coulomb, and the mass of this object is, let's say, 1 kg. So a mass of 1 kg having a charge of 2 into 10 to the power of minus 6 coulomb is projected in this way at an angle of 45 degree with an initial speed of 20 meter per second, and E, let's say probably I'm going to have 20 times 10 to the power of plus 7 Newton per coulomb in x direction. Okay, let me make it more precise. The electric field is existing in this space in x direction, and the magnitude of the electric field is given as 20 times 10 to the power of 7 Newton per coulomb. Now you guys have to find range of the projectile, or means the range of this object on this horizontal x-axis, right? Okay, fair enough. You can pause the video, you can try it up, okay, or else let's see now how we can do it. Okay, since the electric field is coming up in this horizontal space, you know, now normally what we have seen that there is no force acting in the horizontal direction in the projectile motion, so the uniform motion was existing in the horizontal x direction. But since we have electric field in this x direction, so the body will be having an acceleration in this direction as well. Fair enough? Okay, keeping that in mind, first of all, let us find the time that it's going to take to get the proper height, the maximum height over there. Okay, now we know that h equals ut plus, in this case when the body is going up, minus half gt square. I have no idea about the value of height over here, so I'm going to use v equals u minus gt. At the top point, the vertical velocity vy should be 0, so 0 equals u is how much? So this u will be having two components, one going to be 20 cos 45 degree and one is going to be 20 sine 45 degree, and that's going to be your u y, and this is going to be your u x. The V is 0, uy, let's put it uy, that should be how much? 20 times cos 45 is going to be, sin 45 is going to be 1 by root 2. Let's say g is 10 times of t. So from here what I'm going to get is t is going to be how much? Root of 2. Well, this time is taken up to reach the maximum height, isn't it? So the time period of the flight, the entire flight, should be how much? 2 times of this. This is the, I'm going to write it, time period of the flight. I'm sure you guys have seen the videos of projectile motion. Yeah, I'm sure you'll be having idea of this. If not, you can check my videos. I'm going to upload some videos on this projectile motion as well. Anyways, now knowing the fact that the time taken to complete the entire range is how much? 2 root 2 seconds. Okay, now let us talk about the horizontal direction. So there is an acceleration. There is an acceleration in horizontal direction, right? Horizontal direction. We need to find that acceleration, ax. Ax should be fx over mass. What is fx? Since this is a charged particle with a certain amount of charge, there is an electric field existing over there. We know that F equals to Q times of E, right? Then the force acting in this horizontal direction should be how much? Q, that is how much? 2 times 10 to the power of, let's say, minus 6 coulomb, times E. E is how much? 20 times of 10 to the power of 7. That is the force in the horizontal direction over the mass. Let's say the mass is how much? 1 kg. Let's keep it 1. How much I'm going to get? It's the force should be how much? I'll be having, okay, we can change it. Let's say 2 times this, let's not keep the values higher. I'm going to have 4 and 0, 40. So the acceleration should be how much? 40 meter per second square in the horizontal x direction. Now what we need to find? We need to find the range in this horizontal direction, right? We know the acceleration, we know the time taken up. I'm going to actually find the x movement. Okay, let me have a bit of space over here. Okay, so now the x movement, the distance in x, so the range should be how much? Range should be, we know that x is equals to ut plus half at square, right? If I can write x, that should be uxt plus half axt whole square. Okay, no problem. This x is gonna be the range, isn't it? Ux is how much? 20 cos 45. That's initial velocity. That's 20 times 1 by root 2. Time is how much? Already we have seen, that is 2 root 2 of the entire flight, plus half a. A is how much? 40 times square 2 root 2 whole square. Well, that should be how much? Cancelled up. I'll be having 40 plus, this is going to be how much? 20 times of square of this, that should be how much? 8. So the range should be how much? 200 meter. So the range of the flight should be 200 meter, isn't it? We're going to see a lot of questions on this electric field, guys. I'm going to stop today's lesson here only. I'm going to come up with the next videos and many questions. Just keep watching and keep learning. I'll be coming up with the more good questions. Probably I'll be getting up to the next level, to the maybe probably all these competitive exams. Alright guys, so that's all for today's videos. If you have not seen the previous video of electrostatic force, Coulomb's law, do watch that. That's going to give you a lot of insight about this topic. Fair enough? Thanks for watching. I'm going to see you guys very soon with the next video. See you guys. Bye bye.